of what's happening at the margin, a marginal change in one thing affecting a marginal change in the other thing. In calculus, we're taking a derivative. Every time you see marginal, there's a function behind it that we've taken a derivative of. So we have some big complex function. In calculus, we take derivatives and we get slopes at different points. Okay? So the marginal rate of technical substitution is with our two inputs that we're putting into production. It's the rate at which we can exchange one input for the other input and stay at the same level of production. The technical substitution means substituting between the two inputs that we have. So here is our derivative of the profit function. We have the marginal product of water divided by the marginal product of nitrogen. Marginal, I should put this on there, product. Marginal product of water over the marginal of nitrogen. At the margin, instantaneously, along the slope, how much can be substituted? And at the optimum, we're going to set this equal to the price ratio. Some point of tangency will be equal to the ratio of prices. So going back to a new graph where we have x1, x2, we would have a set of isoquants with increasing levels of production. These are our topographic lines of how much we're producing. We want the marginal rate of technical substitution is this tangency point, and we would want to set that equal. It's hard to draw different lines that just glance each other at some point. We want the marginal rate of technical substitution to be equal to the price ratio. So let's think about this is the curved ones are isoquants, and the straight one is our isocost. There's a couple ways we can think about it. Graphically, the costs are going up as these lines go out, right? This would be higher total cost, this would be lower total cost. So we want to minimize the cost. We want the lowest cost line that matches, these are going up, the quantity lines are going up. So we want the highest production line glancing the lowest cost line. One way to motivate it. So we could say we want to get on the highest isoquant given a fixed cost line. So say we have a cost line, we know how much inputs we can afford, we want to get on the highest production line we could get on. Another way to motivate it is we could say we want to spend the least cost to produce a given level of output. So the least that we would have to spend to produce a certain level Q. The third way to motivate it is this question about slope. We want this marginal trade-off equal to the price ratio. 3 different ways that we're thinking about this. How we're going to pick this bundle that's going to be the least cost point to efficiently produce at Q1, a level of production that we motivated. If we were to produce here or here, which are also producing Q1, but the cost would be higher. These would be higher cost. If we were to produce along the cost curve at here or here, our level of production would be lower. So there's one unique point, one unique bundle, where we would have the least cost for the highest production. The point of tangency. Okay, I'm going to switch it up a little bit. I've talked about the environment a tiny bit just to keep you guys from falling asleep. The Salinas Valley. Anybody here from Salinas Valley? All right. The salad bowl of the nation. Produces some of the most highest value crops in America and in the world at one of the highest productivity rates. Incredible if you ever go down there. You can see it if you drive to, let's say, Santa Barbara or San Luis Obispo on Highway 101. You go through the Salinas Valley and you can see the crops all around. Comes almost all the way to, this is like Monterey and Carmel. Highway 101 is going like this. You've probably driven through there. Some big problems with their groundwater, accumulating from so many years of such high value agricultural production. There's nitrogen, and we would say nitrates in the groundwater. So it's also what we would call non-point source pollution, which we'll get back to later. It's not like a factory with a pipe coming out of it, and you can say, oh, look, this is where the pollution is getting into the river. The groundwater table is totally diffuse and dispersed, and the amount of nitrogen coming off these fields is going in at millions of different places. It's very hard to figure out where the pollution is coming from, how to blame it. They're just now getting data to sort of map where the pollution is exactly. Nitrates in groundwater are a tough problem. They disrupt something in the hemoglobin of your blood. It's one of these things where the actual health effects aren't well measured. We have regulations to say you can't have nitrates in groundwater above a certain threshold. We don't have the exact science on the epidemiology of how it's bad for you or what exactly it causes. One thing it causes is once in a while a baby will come and will be all blue, the blue baby syndrome. So that rate increases. But there's other longer-term health effects from people drinking nitrate-laden groundwater their whole lives. Salinas Valley, 30% of the world's lettuce. I don't know what the is for U.S. lettuce, but it's like 80 or 90% of the United States lettuce. $1.2 billion in the lettuce crop. So this is a huge amount of money and a huge amount of lettuce. There's a study. This has finally gotten to the legislature. The legislature commissioned a study, passed a bill. So these are two. This is Salinas Valley here that we're talking about in Chapter 8. And these are public and small water systems. So this isn't East Bay Mud or like big city water. These are small local community water systems. And these ones in red are milligrams per liter of nitrate. So a whole lot of red wells here that are completely undrinkable along this river valley. Here's the Tulare Lake Basin, Fresno, Visalia, a lot of problems over here as well. A little more dispersed. But we're talking about there are people who this well, or we'll talk about this well right here, this is the well that supplies their town's water supply, and it's polluted. And what should we be doing for those people? So here is just an overlaid map on how much fertilizer is applied on the average acreages here. Again, this is our Salinas Valley that we're talking about, and we can look at what it is let's look at 8.1, I think it is. So there's a rate on the, it's in the next couple slides. There's a rate in this chapter. Yeah, kilograms per hectare of nitrogen. The ones in this book, I just want to point out, are in this range here. Okay, but obviously this is like real world data from, I don't know what year, but contemporary data, and we're talking about down here, right? So a lot of nitrogen is being applied to these fields, and it's getting into the groundwater pretty substantially. There's a town called San Lucas, California, just outside King City. The entire town has not been able to drink the drinking water that comes out of their taps for 3 years. Right? This isn't far away. This isn't Africa. This isn't some other part of the world. This is California. And anybody who lives in this town depends on bottled water that's shipped in twice a week. There's been a farm that's been found responsible, and they pay for the bottled water truck to come. But the big issue for this is schools. So there's like the elementary school, nobody can drink the water there, so they have to have bottled water in the schools. It's pretty acute problem. It's not like a general idea of like there's this groundwater plume. Like these people, it's a very small town, but these people cannot drink the water in their tap. So, all right, depressingly, we'll go back to production. These would be isoquants, looking at how much lettuce we could produce on a hectare of land. Tons of lettuce that we could produce. So these are 3 isoquants that the book has come up with, increasing amounts of lettuce production. We have 2 axes here. We have nitrogen here. And remember, I just wanted to say that in the real world, people are putting this much nitrogen on their land. But anyways, the book's down in this area of its model. And there's how much water is produced. As we motivated before, bundles D and bundles B would produce the same amount of nitrogen per hectare. Point C here, it's inefficient to produce this much. It would cost more than D or B, and it would be applying too much to get this level of output. So again, we can solve this. We have our total cost, which we've already done, and solved for water, based on the price of nitrogen and the price of water. So we've already done this. Now we have an isocost line. It's a little bit low. An interesting thing about this is when we have 1 or 2 of the variables, there's only going to be 3 variables total, so we can solve for where we are, as it points out here. If we start with the intercept being 1,142, right, what do we got here? Just to look at our units. Millimeters per hectare. So this means how much 1 millimeter of water covering a hectare of land. In California, we call it acre feet, but you could say 1 millimeter over a hectare of land. It's a volume of water applied to an hectare of land. And then here we have kilograms per hectare of land, kilograms of nitrogen per hectare, just to think about what our units are. We have applied here 1,142, so that's like a meter, right? A meter of water has been applied to this lettuce per hectare. A meter of water deep per hectare, and then if we find that the price is 23 cents, we can figure out that the total cost here on this low cost line is 262. We could read these other intercepts off, 1229 times 23, and we could get these 3 intercepts off of here and figure out what our total cost lines represent. This one would be 282. This one would be 302. So along this line, this whole line here, this is $262, wherever we are on this low cost line. The medium cost line, $282, wherever we are on this medium cost line. So we assume that the authors had access to some pretty good data from Salinas Valley lettuce production that they were able to put these together with. So we now had 3 isoquants. We started with 3 isoquants of different yields. In agriculture, we would say that the amount that we get off a hectare per hectare, it would be the yield of lettuce. And these are the per hectare costs of lettuce. So we have 3 different price lines and 3 different isoquants. So this is sort of blown up. Again, what they did here is like, if you just look, these don't go to 0, so they blew up the area that we're analyzing in the graph. Point A, this point of tangency, the price line is equal to the marginal rate of technical substitution. If we're over at point E, we're still producing this 3.37 yield, but point E is costing a bunch more. And then just as we derived a demand curve with 3 different points, we can derive a cost curve. So here's our isoquants. Here's 3 different quantities of yield that we'll put in a table down here. And here's 3 different cost lines that will get us to these points. So this cost line is 209, this cost line is 241, this cost line is 282. And that's from a combination of water and nitrogen at their prices. And so importantly, for the next lecture, now we have a cost curve going up. A per hectare cost curve, variable cost increasing. This is the quantity of output and how much it costs to produce that quantity of output. So this is just the motivation of how you get to a cost curve. After this, we're going to say here's a line of cost curves. But right now we're going to think about here's us moving up on isoquants. As we move up on isoquants, the embedded bundles are going to cost more. So we have a question as a regulator, how we're going to reduce the amount of nitrates getting into the groundwater. Right? It's not a technological question. In this chapter, we're just going to say how we're going to change prices behind things. So in the Salinas Valley case, in this book, it's a little counterintuitive. But what the book is saying is that people are putting too much water on their lands. They're putting so much water on that the nitrogen is running away and getting into the groundwater. If they weren't using flood irrigation or furrow irrigation, if they were using drippers that were a lot less water was being used, the nitrogen would move a lot less far and wouldn't get into the groundwater. So in this book, it's interesting to keep the intuition. They're trying to get the water applied down more than they're trying to get it's okay. So in this book, in this example, they're moving from point A to point H by increasing the price of water. When you increase the price of water, this price line shifts where our point of tangency is shift, and we get to a new input bundle. So this is a question of increased price of water to discourage water use. So the new bundle has less water and more nitrogen. We've increased the price of water. One thing that's important if you look at this graph, the actual costs are going up, right? So if you were just changing the price and keeping on the same costs, you would have a line like here. Remember, this point is, what if I spent all of my money on nitrogen? So as the price of water changes, this point wouldn't change. The price of water going up wouldn't affect this intercept. So if we were to just drive up the price of water and stay on the same cost, we would be on this point down here. But the producer is going to add more nitrogen, and their costs are going to go up a little bit to stay on the same yield curve. So this is something you can read off this. You can see, like, oh, this line's, this intercept has moved way out to here. They're spending a lot more money now. Costs have gone up. So this is, they increase the price of water, and then you can see the total costs have gone up a whole bunch. You have taxed water. The producers are paying a lot more for the water. This is the question here. Can you more than double the price of water? They're going to use some less water, but their costs are going to go up a whole bunch. We moved from point A to point H. Their costs have gone up. So this brings in an interesting set of questions. We don't usually control pollution by saying what technology we're going to use. We don't usually go onto the farm and be like, okay, you lettuce farmer, this is how much water you're going to use. A lot of times with pollution, what we do is we say, this is how much pollution we're going to allow. This is how much pollution we're going to allow to come off of your farm or out of your factory. We think that the producers can pick their efficient combinations. So it's really hard in the case of Salinas Valley. We don't really have a good way to measure nitrogen coming off their land, so that's very difficult to measure the rate at which they're polluting. But important, we think it's efficient for the producers and for society to let them find their input bundle. This is sort of underlying it all. We're not going to pick input bundles for them. We're going to let them pick input bundles. They'll know how to find the efficient point. They know their production function better than a regulator would. We can limit how much they produce of something in terms of an output, but we're going to let them find that efficient point. So we have what's called emission standards in cases where we can measure outputs. We have car emission standards. We can take cars that are about to be sold. We can run their tailpipe. We can measure it. You guys have all been to SmogCheck. You can see, like, there's a device that's deployed all over the place that measures the pollution coming out of a tailpipe. For big power plant pollution, we can require them to put measurement on the top of their smokestack that measures how much sulfur dioxide is coming out of their power plant. Now our question is, can we make measurements of how much carbon dioxide and methane are being emitted from individual sources? Right now we have models. If we want to deal with climate change and carbon, we have models because we know roughly how much things are done. But if we're going to put a tax on carbon, if we're going to put a price on carbon, are we going to be able to measure each different source how much carbon is coming off of it? Another way to motivate this is you could have your X1 and X2. You could have one of them be pollution, or that the firm is using the pollution absorbing services of the environment. Right? In air pollution, you could say the firm has all other inputs and clean air. In river pollution, you could say they have, or groundwater pollution, they have other inputs and this groundwater that they're using up. So one way we talk about this, they're using up units of clean. Like the environment has so many units of clean, you're polluting into it, you're using up units of clean. We'll talk about this later when we talk about abatement and efficient levels of abatement. But what we think about is our regulators, we're trying to get a least cost way to reduce pollution. We're trying to get the least cost put onto the producer to reduce pollution. So here's some examples. If we think of clean air services, we produce coal with coal and the ability of the environment to absorb carbon dioxide and sulfur dioxide. The ability of the environment to absorb sulfur dioxide was running out because lakes were dying, acid rain was killing off nature in the East Coast. We ran out of the clean air services for sulfur dioxide. They had to start to pay for them. Right now, our entire planet is running out of the ability to absorb more carbon dioxide. So we need to price the ability of the planet to breathe in carbon dioxide. So you could say a car uses gasoline and clean air services in terms of ozone and nitrous oxide. Los Angeles used up their clean air in the 70s, and they needed to price the clean air by requiring people to buy cars with catalytic converters that costed more, and they needed to price the ability of the environment to breathe in these outputs of gasoline production. So you can say lettuce is other inputs and clean groundwater. Just to motivate this, if we have an isoquant, we could have all other inputs into production and pollution. And we want to move from one level of pollution to another level of pollution along an isoquant. How do we find an efficient bundle that gets us a least cost way to get to this other point? So one is taxing the pollutant, right? Here, the pollution isn't costing them enough. We're going to change from this price line to this price line. We're going to say pollution's going to cost you more. We need to pay for acid rain in lakes. We need to pay for the clean water in Los Angeles. We're going to make pollution cost more so we get our price ratios different and we get a lower level of pollution. But this can be really hard sometimes in groundwater pollution or car exhaust. It can be really difficult to price the pollution itself. We can't actually find each emitter of each car and track them and say how much each person is emitting. So there's a different